We're going to discuss first order linear equations. These are not real hard. If you take the differential equations class, this is one of the first things you'll do again, but you'll do it in more detail. The most common form for expressing a first order differential equation is because there's an existence uniqueness theorem for solutions to this when given together with an initial value. Remember, DEs stands for differential equations. These are equations for an unknown function that satisfies an equation with derivatives in it. So the most popular form of these is standard form because of the existence uniqueness theorem that we won't cover in this class. It's always nice to know when you write up a model that it has a solution and it's unique. You hate to say the airplane flies two different ways or something like that, or has no solution, flies into imaginary space. It's fun for sci-fi, but not for the FAA. So the most popular form of these is standard form, and it looks like this: dy dt plus p of t times y equals q of t. And let's assume that it's in standard form with p of t and q of t continuous. That's part of the existence uniqueness theorem. Call that equation 1. That's going to be our main equation for today. How can we solve this equation for the unknown function y, on which we suppress the of t, but it's a function of t again, right? This is a differential equation for an unknown function y of independent variable t. What function could it be that satisfies this kind of equation? Well, this is what you do. For these, here's the derivation. This provides some insight, so I think it's worth doing. We let mu of t, or just mu, be e to the integral of p, which we know exists because p is continuous. Its integral exists, right? That's one of the nice theorems why we study continuities. There's all sorts of important things like the intermediate value theorem and so forth that depend on it. One of the important theorems is if p of t is continuous, then it's integrable. This integral exists. We may not know a standard function for it, but we know that there is some function. All right, let mu of t be this thing here, be called an integrating factor. Why would it be called an integrating factor? There's a very good reason. For equation 1. Then multiply through by mu, and you'll see why. We get e to the integral p of t dt, that's mu, times dy dt. Maybe let's write it first order as we did. Let's say mu times dy dt plus mu times py equals mu times q. And now I'll suppress the of t on everything just to save writing of t over and over and over. And if you think about it, this actually has an important property. I'm going to use the fact that d mu dt, this is Greek letter mu, mu, is what? What is the derivative of this? You think of this as e to the u, not mu. The derivative of e to the u is e to the u times u prime, right? So it's e to the u times the derivative of u equals this stuff. Well, the derivative of the integral is just of p is just p, right? So d mu dt is e to the mu times mu is equal to p of t times mu. All right? So the derivative of mu is p of t times itself. That means that this is mu prime. And the left side is actually a product rule, right? This is the derivative of mu times y. You see that? Let's write it this way, I guess, d dt. And let this one as be mu dt. Mu times y prime plus mu prime times y. That's the product rule for the derivative of mu times y. Equals the right-hand side mu times q. That's why it's called an integrating factor, because when you multiply through, this becomes a derivative and you can integrate. So let's integrate both sides. And get the integral of the left equals the integral of the right, right? If the two functions are equal, their antiderivatives are the same, but within a constant. And what is in the integral implies there's an arbitrary constant here. Integral of the derivative on the left just gives you the integrand back, mu y, right? These two undo each other. Equals integral of mu q dt. And now divide by mu, and you get mu equals, mu y equals 1 over mu integral mu q dt. That can be equation 2. What we've just shown is that an equation of the form 1 with p and q continuous. We also assume q is continuous, so this could be integrated. An equation of form 1 with p and q continuous, this is the form of solutions. If we apply this together with an initial value, y of some number t0 equals y0, then we can actually show this provides a unique solution. Now, what often happens, instead of writing down the formula completely too, we'll use this one. We'll just multiply. Let's say this. What's easier to memorize is this integrating factor. Let's write it this way. And if you can just memorize the integrating factor and multiply through by it, you can put it in this form and get to this solution without memorizing this longer formula. So there's two ways actually to solve equation 1. The first one is A, you memorize the integrating factor. Mu equals e to the integral p of t dt. And multiply through by it. And apply the product rule, as we did here, for a generic differential equation. But you can do it to a specific one, is the idea. The second one, so that's essentially deriving formula 2, is just apply formula 2 directly. It gives you the solution straight off. I don't think the book points that out, but it does. This is a lot like when you had to solve quadratic equations in algebra, right? How could you solve quadratic equations? One way for general quadratic equations was to complete the square, right? You could go all the way through the steps where you finish the square and you subtract over and square root plus or minus, and you get the solution. Or if you applied completing the square to a generic differential equation, quadratic equation, x squared plus bx plus c equals 0, completed the square without knowing what a, b, and c were, you came up with the quadratic formula and said, wait a minute, instead of completing the square every time, I could just apply the formula. This is an analogy to that. You can either memorize the integrating factor, multiply through and apply the thing, just like here you can complete the square and solve it, or you can just apply the formula just like you can apply the quadratic formula here. So it's the same kind of thing. There's a long way and a short way. The short way requires memorizing the formula, a bigger formula. This one's short. Formula 2 has to come with the integrating factor. You still have to memorize the integrating factor, but you also have to memorize this formula too. Let's try an example then. I use t here. The book actually uses x, I'm remembering, but for the independent variable. Suppose I give you this one, dy dt plus 4y equals e to the minus 3x. And I just say solve this. This means find the form of all solutions. The form of all solutions, written in the usual way that I'll show you shortly, of a linear equation like this is often called the general solution. So I may say that term. Find the general solution means form of all solutions in terms of, in this case, an unknown constant. How can I solve this? Well, I notice this is dy dt plus a function of t only times y equals a function of t only. It doesn't actually have to have t in here. It just has to not have y in here. So it can be a constant and it's still a function of t only. We'll call this p of t and this q of t. Let's use by method A the integrating factor. And by the way, one of the reasons the book takes the trouble to make you go through the integrating factor and over, instead of using the formula. The formula is real great for these first order equations, but it turns out in differential equations class that you can apply an integrating method more generally for higher order equations and for other first order equations than this. So this technique illustrates making a product rule that works more generally than for this specific equation. This is a really important equation, but if you get used to this technique, it's kind of like when you learn completing the square up here, you didn't use always quadratic formula. Why not? Because then when you went to do other things like equations for ellipses, you needed to complete the square to solve the ellipse equation. And there's lots of other things like that where you need completing the square without the quadratic formula. Similarly here, there are other problems in differential equations where you need to find the integrating factor, but it's not for this specific equation. All right, so by A, let's try the integrating factor to learn that method. Mu equals e to the integral of whatever p of t is. And by the way, it's very important, just like when you use the quadratic formula. If I use this one, 2x squared minus 3x equals 5, and I said, oh, this must be A, B, and C, I know what the answer is. It's minus B is 3, plus or minus square root B squared, minus 4 times A times C, all over 2A. I just missed the answer. What's wrong?
It's -5.
Yeah, C's on the wrong side. It's actually -5. You have to put it into the form with 0 on the right or it doesn't work. Similarly here, you have to put it with lead coefficient 1 and this one on the right or it doesn't work. So make sure this is 1 and the function without y in it is on the right. And it's actually a linear equation, right? dy dt plus p of ty equals q of t. So it has to be exactly of that form. This is another reason you do the integrating factors. You can see if you boo-booed here. Or if you just apply the formula blindly, you can not realize it. So I really like the formula in the long run, just like everybody likes the quadratic formula. So we'll say the integrating factor is e to the integral of this, seeing that it's in the right form, 1 here and this function without y on the right-hand side. E to the integral 4 dt is e to the 4t. And you know what, we get it. We got a plus a c. What are we going to do with that plus c? Turns out what you need for this problem, what we showed in here actually, is you can use any integrating factor. So pick the one that's easiest here. I'm going to choose c equals 0. You can put a plus c on here, but then you got to carry it the whole way, and it still works, but it's just more writing. Well, I'll choose this one, e to the integral, or e to the 4t. Multiply through by this, and I get e to the 4t dy dt plus e to the 4t times 4 times y equals e to the 4t times e to the minus, oh, I used t again, didn't I? Let's use t on this. I put e to the minus 3t. The book says x, but I'll use t. I'm just used to it, I'm sorry. Maybe we'll do x on the next one, e to the minus 3t. So I multiply the equation by e to the 4t, and then I'm supposed to recognize that there's going to be a product rule on the left. This always works, so you check it out. This is how it checks that you didn't blunder back here. This is e to the 4 times t times derivative of y plus derivative of e to the 4t times y, right? So the whole thing is the derivative of e to the 4t times y. It should always come out on the left when you multiply through that you have the derivative of the integrating factor mu times y. That's what we had up here. The left should always come out to be d dt of mu y. Now the other side simplifies here. E to the 4t times e to the minus 3t is e to the 4t minus 3t, or e to the t, right? Exponents add, and you're left with t. Now we're pretty close, actually, once we recognize the product rule. We'll say integrate both sides and get e to the 4ty on the left equals integral e to the t on the right. Well, this one is just e to the t plus a constant, and this constant you do need. What we showed in the method is that any integrating factor works. You can pick whatever constant you want, but to get all solutions, remember, you have to put the arbitrary constant here or you won't get them all. So the right side is e to the t plus c, and the left side is e to the 4t times y. Divide by e to the 4t, or rather multiply by e to the minus 4t. And you get y equals e to the minus 4t times e to the t plus c. Here is what we call the general solution. All solutions to this linear differential equation are of this form. Y equals a constant times e to the minus 4t plus e to the minus 4t times e to the t is e to the minus 3t. You have a solution to the differential equation if and only if it's this for some c. And for a first order equation, the general solution is always a constant times one function of t plus another function of t. This could be 0 that you add, but that's what we call the general solution when you put all solutions to this form: a constant times one solution plus another. Constant times one function plus another function. Well, that's like completing the square, doing all the steps in between. Alternatively, let's just apply the formula too that we derived. And we'll get the same solution. So by equation 2, once again, you have to compute mu just like we did here. We'll say it's e to the integral of p of t, where p is 4. dt is e to the 4t. You pick any constant you like. I'll pick 0. And then immediately, by formula 2, this is y is 1 over mu integral of mu times q dt, just like that. So it's 1 over e to the 4t integral of e to the 4t times the right hand side was e to the minus 3t dt. Let's see. It's e to the minus 4t on the outside times integral of e to the t is just e to the t plus a constant. There it is. It's c e to the minus 4t plus e to the minus 3t. Same thing we got before, a little less work. That's what this whole section is on, and applications. It likes to do a bunch of applications. A lot of these are not pertinent to anybody's particular major, so I hate to spend too much time in the applications. But we do want to do a little of them just to have a feel for what these things can do. Let me first do another practice example here. This is number 5. I'm doing problems off your homework, so when you go back to do the homework, look at these. I probably already wrote it out for you on half of these. Suppose I gave you x plus 1 squared, x squared plus 1, excuse me, times dy dx plus xy equals 0. How about this first order equation? This is actually a linear first order equation. What am I going to do with that? Let's try the same method. Hey, what's an integrating factor for this one? I start to say mu equals e to the integral of x dx, but that's wrong. What's wrong? First, have to write it in standard form, right? So I'll divide by x squared plus 1 and say equivalently, in standard form, this is dy dx plus x over x squared plus 1 times y equals 0 over x squared plus 1 is still 0. There it is in standard form. 1 multiplying dy dx. The function without y in it on the right. All right. Now, this is our p of x. We'll write in terms of x this time. So the integrating factor mu is e to the integral of p of x dx is e to the integral x over x squared plus 1 dx. Let's see, how do I integrate x over x squared plus 1? All right. I know if you have a function of a function, like here I have division by this function. If I let u be that function, maybe it'll get easier. Now it's just 1 over u instead of 1 over s. If I do that, though, I need du to be the derivative dx. Right? It needs to be du dx dx must be 2x dx. And luckily, that's a multiple of what I see multiplying dx. If du is this, this tells me that 1/2 u, 1/2 du, can be used to replace x dx that I do see. Well, I'll scratch this out and put 1/2 du. And I'll scratch this one out and put u. What I got then is e to the 1/2 integral 1 over u du, which is e to the 1/2 natural log u. Absolute value doesn't need to be on here. Why not? U is x squared plus 1. It's already positive. So I'll leave the absolute value off. Well, properties of logarithms, this is e to the ln of u to the 1/2, right? P ln u is ln of u to the p, recall? E and ln undo each other, so this is just u to the 1/2. It's square root of u if it's an integrating factor. Knowing that square root of u is an integrating factor, we can multiply through, and the left side will become the derivative of a product. It always works, right? We proved it. So this says now multiply by integrating factor mu, and I've got not the first equation, but I multiply the one in standard form by that. U to the 1/2 times mu, excuse me, 1/2 times dy dx. Oh, and here's this is mu. I also need mu prime. Well, let's just go ahead and write this. Maybe I should write this. Let's write this as x square root of x squared plus 1. Because 1/2 power is square root and u is x squared plus 1. Let's write it that way. Now multiply by mu and get square root x squared plus 1 dy dx plus square root x squared plus 1 times x over x squared plus 1 times y equals square root x squared plus 1 times 0. if I did this right, this will be the derivative of mu times y. Let's see. Mu is x squared plus 1. That multiplies y. Is that the derivative? And the whole thing equals 0. Well, first one times the derivative of the second, plus this is x over square root x squared plus 1 is in fact the derivative of square root x squared plus 1, right? You get 1/2 this to the minus 1/2 times 2x gives you this. So sure enough, the derivative of this is this as we anticipated. And now that we've got this derivative equal to 0, the integrating factor has made this integral. Well, we integrate. On the left, the integral of the derivative just returns the function x squared plus 1 times y. And on the right, the integral of 0 is a constant. When integrate, you get this. Evidently, y is equal to the constant over square root x squared plus 1. This is the general solution. Again, it's a constant times a function of x plus another function of x. You can think of it as plus the 0 function, right? We don't need to write the plus 0. There is the general solution. So put the differential equation in the standard form before you apply it. Again, we can do the second method. Formula requires still that you compute mu first. Mu equals e to the integral. P of x is x over x squared plus 1 dx. When we integrated this before, let's see, we got square root x squared plus 1. So this is all right, so this one we integrate. This is ln square root x squared plus 1 with some work to do the integral. Same work we already did. So this is square root x squared plus 1. That's the integrating factor. And then the solution is y equals 1 over mu, integral mu q dx. X is the independent variable. Q is the right-hand side here, right? This time it's the 0 function. When it's a 0 function on the right of a linear equation in standard form, we say the equation is homogeneous. So that's a name for it. I don't think they pointed it out in the book, but because the equation is homogeneous, 0 here, it makes it particularly simple. This is just 0 times this, so the integrand is 0. What is the integral of 0? It's just a constant. So this is going to be c over mu, which is c over square root x squared plus 1. There it is, the general solution of the formula. Here's an example of a non-homogeneous first-order equation in standard form. A homogeneous first-order linear equation that we can put into standard form by dividing. Okay. Now we can do some tricks with this. I may need to go get my calculator to bring that on this next one. Well, actually, I've got one more example beforehand, come to think of it. Let's do one more. This one, I'm just going to use the formula. Suppose I had this one. This is number 7. Suppose I wanted to solve x dy dx plus y equals x, this time together with the initial value y of 1 equals 2. Solve this initial value problem. An initial value problem is different than just a differential equation. It has an initial value too. We said before that for existence of uniqueness theorems for nice differential equations, which for these just means you have to have continuous coefficients when you put it in standard form. There exists exactly one solution to a first-order equation given with one initial value in the solution interval. So this is actually going to produce a unique solution. There won't be an arbitrary constant like this. the way we get is first solve the differential equation with the arbitrary constant, then plug this in to determine what the arbitrary constant is. And this is what happens in practice in mathematical modeling. You know that the solution, the position of the object flying through space or whatever it is, the current going through the circuit satisfies the differential equation, and you know what your initial charge was, or initial current was, or initial position of the object was, and between the two, it determines exactly the velocity of the object. So what we do first is we put it in a standard form by dividing the differential equation through by x and write dy dx plus 1 over xy equals 1, together with the initial condition. Now to solve the differential equation, we call this p of x and call this q of x. We'll say that an integrating factor, you multiply this through by to make the left of product rule, it can be integrated, derivative of product, is mu equals e to the integral of p of x, 1 over x dx. What's the integral of 1 over x? We remember that's natural log absolute value of x plus a constant, right? But there's a subtlety going on here. I can drop the absolute value again. Why? It's positive. Here's how you know. Yeah. The original differential equation written in its standard form isn't defined at x equals 0. So you have to solve this on the interval 0 to infinity or minus infinity to 0. You have to avoid the 0 point when you solve this. Now you don't actually technically here, but then there's an ambiguity at 0 that we're going to avoid by starting with standard form. But we're going to find all solutions on one of these two intervals. Which one? It has to be the one that includes the initial condition. This says when x equals 1, y equals 2. That's what this says. If you want to pick the interval that includes x equals 1 to guarantee the unique solution, I have to choose this interval. If I choose this interval, I can drop the absolute value. So what happens is we'd have to have the absolute value or else put minus x here if the initial condition was at minus 1 or minus some negative number. But since it's a positive number, I can just drop the absolute value. It looks like this. E and natural log undo each other, and you get the u is actually equal to x, an easy one. All I got to do is multiply back through x. It was already integrable. What a mess, huh? So I did all that work to find out it was already easy. I put this back by multiplying through by x. I get x dy dx plus y equals 1, and recognize now this was already a derivative of the product, right? Before I got started. But at least the integrating factor showed me that, right? Now I try it out and say this is equivalently the derivative on the left will always be of mu times y. So it should be x is the integrating factor times y, is it? And on the right I have x still. Yeah, and I multiply this through by, this isn't 1, this is x. I multiplied through by this one by x and get this equals x. And sure enough, let's see, x times derivative of y plus y times derivative of x. Yep, the left side is the derivative of this product, mu times y, as we proved it would be. So now you integrate, and you get xy on the left equals, the integral of x is x squared over 2 plus a constant. You have to put the constant this one and you won't get all the solutions. Now you can divide through by x and you get y equals x over 2 plus a constant divided by x. That's the general solution of the differential equation. That's what we wanted, was not the general solution only, but we want to find the unique solution when there's also this initial value applied. So you apply y of 1 equals 2. That is to say when x equals 1, y equals 2. Put it in and get 2 on the left equals 1 over 2 plus c over 1. evidently by subtracting a half over, we find that the only value for C is C equals 3/2. That would have been predicted by the existence uniqueness theorem. When it says that when the P of X and Q of X are continuous, any initial values whatsoever in the solution interval provides a unique solution. So this is in the solution interval, X equals 1. And these are continuous in an interval 0 to infinity, so we will get a unique solution on 0 to infinity, guarantees. Again, you don't need to learn the existence uniqueness theorem. I'm just pointing that out for your education. With C equals 3/2, we'll say, therefore, y equals, putting C equals 3/2 in here, x over 2 plus 3 over 2x. That's the unique solution that satisfies the differential equation, and also that y is equal to 2 when x equals 1. Okay, there it is. That's the whole thrust of the section. That's what I really want you to get out of this. You just be able to solve these kinds of problems. Linear differential equations with or without an initial value applied. Well, there's another one we can do here, though. Emphasizes something from the last section that I wanted to put in. That's number 19. And it says, use Euler method with a step size of delta x equals 0.2. This is what I need the calculator. Remember Euler's method last time? Why Euler's method? With step size delta x equals 0.2 to numerically estimate the solution to y prime equals x plus y. That comes together with the initial condition y of 0 equals 1. Since it has an initial condition, we're going to get a unique solution. Let me grab my calculator real quick. Now, a computer can't run forever, so we have to put some solution interval which is supposed to end here. And on the interval 0 to 1. So these x goes from 0 to 1. And then we're going to compare this with the exact solution. So part A will say, the Euler's method is to say, this one, you set for y prime equals f of xy together with y of t0 equals y0 with some step size, constant step size delta x. It doesn't have to be constant in practice. In practice, they shorten the step size when the solution is jiggling real fast, and then they lengthen it when it's doing something slow, so they don't waste time when it's slow and they don't miss something when it's fast. But for us, we'll just use constant step size delta x. What you do is you set y0 equals y naught. This one's a 0, this one's a naught. We'll say y of t naught equals y naught. That's what I should have said. And t0 equals t naught, the initial condition. And then for k equals 0, 1, up to whatever number of steps you're going to take, n steps, you take t0, t k plus 1 equals tk plus delta x, and under delta, oh, using t again. I guess I better use x and say y of x naught equals y naught, step size delta x, t x naught, x0 equals x naught, y0 equals y naught, there we go. So xk plus 1 equals xk plus delta x, and then y, that increments x each step, and then yk plus 1 equals yk plus delta x times f of xk, yk. That was Euler's method from last time. And you do that over and over till the end. So what I'm going to do first here is apply the initial conditions. X0 equals the initial value of x0. Y0 equals the initial value of y1. Then I'm going to try this with k equals 0. I'm going to compute x1, x0 plus 1 is x1 equals x0 plus delta x. Well, let's see, x0 was 0 and delta x was 0.2. And I get 0.2. Now, y0 plus 1 is y1 equals y0 plus delta x times f of x0, y0. And this is your f, whatever y prime is equal to in the equation. Whatever function of x and y. So this is actually y0 plus delta x times x0 plus y0. And we have those from the last step. So this is, let's see, 1 plus delta x is 0.2 times x0 was 0 plus y0 is 1. It's 1.2. And so x1 is 0.2, y1 is 1.2. And you just apply that over and over. It's a machine algorithm. So now we put k equals 2. We finish the loop. We come back down with k equals 1. And we say x, when k is 1, that's computing x2 on the left, is x1 plus delta x. We just increment x. Is 0.2 plus 0.2 is 0.4. Y2 is y1 plus delta x f of x1 y1. But f is x1 plus y1. So this is y1, which is 1.2, plus delta x 0.2, times x1 plus y1 is 0.2 plus 1.2. And let's see, now we got 1.2 plus 0.2 times 1.4. Oops, turn it on, didn't it? 1.2 plus 0.2. Now I wind up with 1.48. You can program these things to do this, but for 5 steps I wouldn't bother. I don't think it's worth it in general. But now we're building up this table of estimated points on the solution. 0.2 with 1.2. 0.4 with 1.48. Let's try one more step. Maybe I'll cut it a little short here and not do the whole problem. K equals 2 means you compute over here. X3 equals x2 plus delta x. Is 0.4 plus 0.2 is now 0.6. So x is just going 0, 0.2, 0.4, 0.6. It's just incrementing along. But the y's have Euler's formula here. Y3 is y2 plus delta x times f of x2, y2. But f of x2, y2 for this problem is x2 plus y2. So we have y2 1.48 plus 0.2 delta x times, let's see, 0.4 plus 1.48. And what do we get out of that? 1.48 8 0.2 times the quantity. So just put 1.88, huh? Now I'm going to put 1.856. There we go. I'm going to stop there and say, when you do it on the homework, you can stop there if you want to. I want you to learn the method, not be a machine. So the solution then, so we could change it to 0 to 0.6 or something. The numerical solution, the estimated solution by Euler's method, can be encapsulated in a table, k versus xk and yk. 0, 1, 2, 3 we computed. Initially, we put the initial condition, 0, 1. Then we had 0.2, 1.2, 0.4, 1.48, and 0.6 with 1.856. So estimated points on the solution curve, the actual solution is a function, right, that satisfies the differential equation. There's Euler's method approximating that last time. Now solve the initial value problem exactly and calculate the error and percentage error in each of the approximations. So B, find the solution exactly. And I'll give you a little clue on some terminology. In numerical methods, when you find the actual solution, you call it the analytic solution, as opposed to the numerical solution. It just means the solution, the real solution. Analytics. So find the analytic solution and use it to analyze error, let's say, in the error in Euler's method, because that was an approximation. So the solution exactly now is like this. We had dy dt, dy dx equals x plus y, as I recall. Make sure I got this right. And y of 0 equals 1. Oh, we can't separate variables like last time. They don't separate, right? If it's a function of x times a function of y, we can separate variables. Fortunately, this time we learned linear equations. We have to put it into standard form. So we'll subtract y from each side and get dy dx minus y equals x. Why did I have to do that? It's because now it's dy dx plus a function of x times y equals a function of x only. That's the form we need. You can take minus 1 as p of x and x as q of x, and now you say it's into standard form as the form 1 with initial value. So we say an integrating factor, if we do the integrating factor procedure instead of the direct formula, or even if we do the direct formula, is e to the integral p of x dx is minus 1 dx. So it's e to the minus x, and you can add a constant in there if you want. In the exponent. Multiply through by e to the minus x, the integrating factor. To get a differential equation where the left side is a derivative by the product rule. You get e to the minus x times y minus y times e to the minus x equals x e to the minus x. There it is. The left side should be the derivative of mu times y. And sure enough it is, right? If this is ddx of e to the minus x times y, right? The first one times the the derivative of, let's see. Differ by a minus sign here. Oh, I know, let's see. That's okay. Oh, this was dy dx, I just wrote it this way. All right, so this one is the first times the derivative of the second, plus derivative of the first, e to the minus x, times the second y. Let's write it in that order, then it's obvious. It's the derivative e to the minus xy as it should be. Equals x e to the minus x. So now we integrate, you multiply by the integrating factor so that you can integrate. The left side then becomes e to the minus x times y, and the right side becomes the integral of x e to the minus x. Fortunately, we have learned how to do this kind of integral, right? What is this one? Pi. Integration by parts, right? When you have a small power of x times an exponential, a sine, or a cosine, you can try integration by parts. We can let u be x and dv be the rest, and this will lower the power of x. So we'll say this is uv minus integral v du, where u is this and dv is this, tells you that du is the derivative of this dx, it's just 1 dx, and v is the integral of e to the minus x dx, that is the integral of e to the minus x dx, v equals that, is just minus e to the minus x, plus a constant if you want, but it falls out so you don't need it. So it's u is x, v minus e to the minus x, minus integral v minus e to the minus x du. So this is minus x e to the minus x, plus the integral e to the minus x is minus e to the minus x. And then there's plus a constant, you have to get it when you drop the last integral sign. Well, if e to the minus x times y is this, we can multiply by e to the x. You get y on the left by itself is then e to the x times minus x e to the minus x is minus x. Minus e to the minus x times e to the x is minus 1 plus c e to the x. And there it is, the general solution to the differential equation. But it's an initial value problem. We need y to equal 1. So now we plug in the initial value. Y of 0 equals, the initial condition we call it, y of 0 equals 1 with the initial value 1, x equals 0, to get, well, with 0 for x and 1 for y, we've got 1 equals minus 0 minus 1 plus c e to the 0. Says e to the 0 is 1 here. So you add 1 to both sides and you get 2 equals c. And finally, putting that in, y must be equal to minus x minus 1 plus 2 e to the x. There it is. Yeah, okay. Sure, I got this right here. Yeah, I think so. Okay. this is the exact solution. We can compare with the numerical solution at x equals 0, 0.2, 0.4, 0.6, yet k, xk, yk, the Euler numerical solution, and y of xk will be the analytic solution. So when I write this notation, this means Euler's method. This means the actual analytic solution. So we had before 0, 1, 2, 3, 0, 0.2, 0.4, 0.6, 1, 1, 1.2, 1.48, 1.856. And let's plug in for this one now. We plug in 0, we get 1 as we expected. If we plug in 0.2, we've got minus 1.2. This. Plus 2 times e to the 0.2. And we get about 1.2428, blah, blah, blah. And then similarly, when k equals 2, we put in 0.4, and we get minus 1.4 plus 2 times e 0.4, about 1.5836, and minus 1.6 plus 2 times e 0.6 gives us about 2.0443 and some other stuff. Let's just do that one. All right, so there's the exact solution to a certain number of decimal places. 3 digits, 4 digits past the decimal point. And so the error, we're going to call it EK. Is y of xk, the actual solution, minus yk, the estimated solution. What you do in the math method, you just have to subtract these. You take this one minus this one, and you get 0. There's no error in the initial condition. We just plugged it in. But this one is 0.04. Line through here. 0.0428. This one is 0.1036. And some other stuff. I'm not rounding. There's some other digits that I took round. And 1.8 to 2.85 to 2.04 is I better subtract it. Be careful. 2.04. Oh, I just have it already. Never mind. Answer minus 1.856. I don't remember the next digit, but it's about 1.88 or 0.1882.
So you were saying the y of xk is the notation for the analytic solution and y of k is for Euler's?
Yeah, because y of x is the solution. If this is the values of xk at the incremented values, then y of xk represents the solution function y of x at that point. Well, yk is the Euler's. So this is y1, y2, y3, y4. This is y of x1, y of x1, y of x2, y of x3. Okay. Now that's the error. They also say find the percentage error. The percentage error is this. It's the error divided by the solution that we call the relative error. Absolute value is usually what they mean. Not necessarily on this one, I'm not sure. Let's leave it not absolute value. Sometimes they just mean absolute value of the percentage. And then times 100% to convert it to a percentage. So it's what we call the relative error, the ratio of the errors of the solution, put as a percentage. We'll just compute that. We'll take this one. Oops, not YKY of XK, the exact solution. This one divided by this one times 100%. So the first error is 0. The second one is 0.0428 divided by 1.2428. This, I wrote this wrong. Oh, that's right. Okay. And then times 100. We get 3.4% roughly error. This one, 0.1036 divided by 15836 times 100 is this, about 6.54%. So about 6.54% of this estimated solution here is it's about 6.54% off from the true solution. 0.1882 divided by 2.2 times 100 gives us, see, so it's increasing a little, 9.2, let's just put 6.5% there, 9.2% error here. All right, so there's the percentage error. To sketch the exact solution and the approximate solution together. Now what you do is you start them both at 1, and then there's 2. This one goes up just above 2, so it's by the time you get to 0.2, 0.4, 0.6, this one has gone up like that. And the other one is just a little bit under it, making just a crude sketch. It's a little under it, getting further and further apart. Right here, right here, right here. And this is the point, 0.6, 1.856. This is the point up above it, 0.6, 2.0442. And so there's a numerical solution. Maybe I should make that in red. Is these points as getting further and further off till they're almost 10% in error, 9% error at the end here. This is common. Here's what's happening in Euler's method. Euler's method is taking the actual analytic solution and taking a tangent line to it. Then there is another solution of the differential equation, not with the same initial value, an integral curve we call it, and it's taking the tangent to it. And then it's taking another integral curve that goes through that point as initial value. And it's taking the tangent to it. And it's taking those sequence of tangents, and here's the numerical solution, just those points. But those tangent lines, the solution curves that had different initial values, are throwing us further and further off. Because this is concave up, Euler's method is successively underestimating it. If this becomes concave down, it will start to come back towards it. As you can kind of see how the numerical methods work. This is a very simple one. So maybe we have time for one more problem here. This is number 21, which I'm also assigning. Tonight I'm doing mostly homework problems that I'm assigning for you to look at. So you can go back and look at these. Was there any more discussion before I erase all of it? I'm sorry, I erased it too soon, maybe. Get rid of this. Last one is an application, then. It's a mixing problem. Some people in chemistry may take an interest in this kind. So these are lots of applied problems here. Differential equation is a very applied subject. Suppose at time 0 a tank of water and salt mixed, so it's a brine, contains 25 ounces of salt dissolved in 50 gallons of water. Now, the brine containing 4 ounces of salt per gallon, brine just means a saltwater mix. So it's a homogeneous mix, it's all been stirred up. A brine contains 4 ounces salt per gallon. Enters at 2 gallons per minute. Into the tank. And a well-mixed brine, right, is mixed in the tank, exits at the same rate. You pour in a salt with a different concentration, or a brine with a different concentration, let it mix up and pour something, let it leak out the bottom. Exits also at 2 gallons per minute. How much salt was in the tank at time t? Arbitrary time t. This is a differential equation problem because it's a rate problem, showing you what kind of things you can get in practice. I think it's worth drawing the picture. You have a tank. Doesn't say how big it is. Wait a minute. I'm sorry. Yes, it does. 50 gallons. And the idea is there's a tube coming in, pouring in at a rate of 2 gallons per minute. This brine at a different concentration. And then there's a hose coming out that's pouring this out at 2 gallons per minute after it's mixed. How can I solve this one? Here's the trick to solving these mixing problems. You write rate in equals rate out. Start with that equation. Now, what's the rate coming in? Rate of salt in, I should put, because it asks how much salt is in the tank. Equals rate of salt out. The salt is coming in. Well, the mixture is coming in at 2 gallons per minute. I'm going to let y of t equal the salt in the tank at time t. So I'm going to go back to t as my independent variable, t for time. Then we'll say that dy dt is ounces of salt in, and this is ounces of salt per minute t. That's the rate salt is coming in. It has to be equal to the rate that salt is going out. This is, oops, I didn't write this right. Or what's your basic equation wrong? It should be this. dy dt, the rate at which salt changes in the tank, is rate the salt is in minus the rate is out. I'm sorry. Rate salt in minus rate salt out. There we go. So dy dt, which is ounces of salt per minute, is equal to the rate the salt comes in. What rate is it coming in? It's coming in through this pipe at 2 gallons per minute times the brine that's coming in is 4 ounces of salt per gallon. That's the rate at which it's coming in. Then you have to subtract the rate the salt is going out. You say it's going out at 2 gallons per minute. And the fluid is going out 2 gallons per minute. With a well-mixed version, what's the rate? What is the concentration of the salt that is going out? It's Y ounces of salt per a 50-gallon tank. It keeps constant 50 gallons in there because it's going out at the same rate it's coming in. So it's always got 50 gallons. So Y ounces per 50 gallons is the concentration of the well-mixed thing in the tank, goes out at 2 gallons per minute. Here's the rate at which it's going out. Now we can simplify this and write this as equivalently as, but you check your units, ounces per minute, cancel the gallons, ounces per minute, cancel the gallons, ounces per minute of salt. I really should write ounces of salt and gallons of brine. Cancel the brines anyway, but just to save writing, I'll do it that way. dy dt equals 2 times 4 is 8 minus 2/50ths of y as 1/25 y. There's my differential equation. Now there's one more thing. It starts with 25 ounces of salt dissolved in 50 gallons of water. So since y is the ounces of salt in the tank, we know that y of 0 equals 25 initially. That was given. Now it's an initial value problem. We can tell you exactly how many ounces of salt are in the tank. That's part A, is just to set it up. Oh no, I'm sorry. It's also solve it part A. We'll just do part A tonight. And we'll say that's a linear equation, right? If we rewrite it equivalently as dy dt plus 1/25 y equals 8. This is your P of t, and this is your Q of t. I can solve this immediately by the formula. By B, I can say mu equals e to the integral of 1/25 dt. Right? Integral P of t dt is e to the 1/25 t. Now the formula for the solution is y equals 1 over mu integral mu q dt is is 1 over e to the 1/25 t times integral e to the 1/25 t times 8 dt gives me, let's see, e to the minus 1/25 t. Integral of e to the 1/25 t is e to the 1/25 over 25, gives you 25 times 8, or let's write it that way, 25 times e to the 1/25 t times 8 plus a constant from the integration gives us, well, let's see, these cancel. We've got 25 8 times 8 is 200 plus c e to the minus 1/25 t. evidently, the amount of salt in the tank is going to decrease exponentially with exponent minus 1/25. So now we apply the initial value that y of 0 equals 25. So we plug that in and get 25 on the left equals 200 minus c times e to the 0 is just 1. Says that c equals 175, and our unique solution, the amount of salt in the tank at any time t, is y equals 200 minus 175 e to the minus 1/25 t. What you observe is that this thing decays exponentially towards 200 ounces of salt in the tank, beginning with 25 ounces in the tank. Okay, that's it. Try these on the homework problems then at a time. 8.4. We did a bunch of these this time. 1 to 9 odd. Those are separating, those are linear equations and linear equations with initial conditions. And then the two applied problems we did, 19 and 21. Maybe I'll ask you something like that on the final.